So yes, today this is my talk. I believe at this time of the evening, I don't have to convince you how incredible your brains that actually brought you here tonight is. This very brain or machine that is responsible for some of the great abilities of us as humans, such as creating music and solving problems and exploring the universe and chatting and building sophisticated machines and dancing and so on and so forth. But I do want to talk to you today about what happens when this machine goes wrong. What happens, for example, in stroke conditions? How do we explore brain damage? What happens when the ability to speak, for example, that connects us as humans suddenly disappears? And these are the kind of questions we are trying to solve in our lab. I want you to travel with me back in time to the 19th century. The year is 1861. And this is a French neurologist named Paul Broca, who met a patient named Tan that would change science forever. Tan, this patient, had a stroke, which is a condition when blood supply to the brain is disrupted. And when this happens, certain regions in the brain lose their oxygen, which leads to their death, actually. And this is what we call stroke or brain damage or brain lesion. Why this patient was called Tan? Because after he suffered from a stroke, the only sound he could make was tan, tan, tan. I want to show you an example from our times of a patient with a stroke and language difficulties that are similar to tan.
But tell me, why is it that you...
I believe I can play with the sound. Yes. So I'm sorry, subtitles are missing, but the speech language therapist basically asked him about moving to a new place.
Moving, actually.
Why are you moving?
Tunnel, 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 tunnel. A tunnel, 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 tunnel. A tunnel, 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 tunnel. Tunnel, tunnel, or tunnel, 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 or tunnel, 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 tunnel.
Is it...
Tunnel, tunnel.
What number is this?
What number is
Tunnel.
this?
Right? Right. Now let's count it out.
1, 2, 3, 4.
Nice, nice. Well, since you did 4 so well, let's go for broke. Let's go up to 20 if we can.
What's up? 1, 2, 3, 4, 5, 6, 7, 8, 9.
This is fascinating, right? Yes. So this patient suffered from a stroke. He can understand language, but the only sound he could make was tono, tono. But when it comes to automated speech, this is a speech that is automated in our mind, such as counting numbers or singing very familiar songs. He is able to articulate the words without problem. This is just a glimpse to the complexity of language difficulties following brain damage. Now let's go back to Broca's patient, Tan. He was not the only one. So over several years of investigation, Broca gathered evidence from more and more patients with speech impairment following brain damage or following stroke. Broca called it aphamie in French, later known as aphasia, which is the language impairment resulting from brain damage. And Broca wanted to know what went wrong in these people's brains, right? But it was the 1860s, no brain scans, no fancy machine, and the only way to find out was to wait until these people died and actually look at their brains. And that's exactly what Broca did. So he performed what we call a post-mortem examination or dissection, and actually looking at cutting the skull and looking into the brain. Just before we going into the results of Broca's brain, I want to spend a moment talking about the brain structure. So here's the brain. You can see we have two hemispheres. We have the right hemisphere and the left hemisphere. And they are interconnected with very thick nerve fibers to communicate between them. This is just the lateral view, so a view from the side where we see the left hemisphere. Now I want to go back to the brain of Broca examined. And these are some of the actual brains that were preserved since the 1860s that Broca examined. And if we take a closer look, you probably be able to notice that there is a damage to the front part of this brain. And Broca thought this region across his patients was critical for speech, a region that is called up until today Broca's area. But importantly, Broca also noticed a pattern. Patients who struggle with speech after damage to the left hemisphere and not to the right hemisphere. And in this time, it was thought that the two hemispheres were symmetrical in their functions, right? So we have two hands and we have two legs and two kidneys. When you lose one, you can still function with the other. But Broca just challenged this idea, or as he put it a few years later, we speak with the left hemisphere. Today, of course, we know left hemisphere is dominant for language and is critical, but we use both right and left hemisphere for language functions via networks and not in isolated regions. But this work of Broca was still very important. It was a turning point because it was one of the first systematic attempts to link between a brain damage and a function. And it really changed neuroscience since then. Now I want to move with you in time. Let's go to the 1917 and imagine if only Broca had access to this machine. So this is an MRI, of course. It's an incredible invention by human effort and collaboration. Yes, we had CT scans before, but CT had own limitations such as low resolution and radiation. And MRI changed the game because it provides detailed, high-resolution, safe, and non-invasive technology to look at the living brain. So now we don't have to wait until someone dies in order to look at their brains. We can just put them in a scanner and look at their brains. I want to give you an example. This is an MRI image of a healthy brain on the right. It's a single slice from the middle of the brain. And you can see clearly that the two sides of the brain are relatively, the right and the left hemisphere, are relatively the same size, the same color, the same shape. Now, on the left side, you see a stroke patient with aphasia. And you might immediately notice that something is different, right? So there is a large ventricle here, and there is a messy, dark, shadowed area here, which is actually the stroke. This is brain cells that are dead. It's relatively easy to detect, but what about this example now? This is also a stroke patient. He also has aphasia, but it's much harder, right? Can you guess where the stroke is? Yeah, it's very small, so some dark dots down there. And in our field of research, being able to identify stroke lesions and brain damage is extremely time-consuming. It requires very high expertise. And this is where AI and our lab comes in. So now that you know what aphasia is, I belong to the Halai Aphasia Lab, led by Dr. AJ Halai. And among the many amazing language-related works we are doing in our lab, I want to talk to you about this project, which is called automated lesion segmentation. So what do we do? What this fancy name actually means? We use an algorithm called NN-Unit with the aim of helping doctors and researchers to identify lesions. And what we do actually, we train the computer to be able to identify the stroke, where the damage is, where the brain, where there are dead cells in the brain. So we give the computer an MRI image like this, and then we show the computer, this is the lesion drawn manually by a neurologist. And then we repeat this again and again and again with many examples of lesions drawn by neurologists of the MRI images. And after thousands of examples we give to the computer, what are the results? So the results are really promising. Here you can see our model, some of our models, and on the y-axis here you can see how good the model is performing. So how well the model matches, the model prediction of the lesion matches the actual manual drawing of the neurologist. The higher the score, the better the results. Each dot represents actually a case in our data set, and you can see that the majority of the dots have a very high score. Now, if we take several neurologists to manually drawn lesions, the agreement between these neurologists is about here. So you can see that our model is performing really well, very close to manual segmentation of human neurologists. Importantly, for those who understand AI, this is external validation. So we trained the model on one data set, but then we tested it on a completely different new data set that the model never met before. So it's like training an athlete running in a stadium, but then testing him in a complete new environment. And it shows the model is not only performing good, but it also generalized to new data sets as well. So now I want to show you real examples. Here's an MRI scan of a patient with stroke, right? And the position is like this at the top. So these are several slices from our brain. And then this is the manual lesion, the lesion manually drawn by neurologists in our study, what we call the ground truth. Finally, here is the model prediction of the lesion, and you can see these two are really, really very similar to each other. So now you may ask, okay, if the model performs just like humans, what do we need it for? So it's faster, much, much faster. It can clear time of neurologists to actually see patients. It's cheaper. But also, if we look at the future, imagine if we have a case of a stroke, for example, we can take a patient into a scan and then give it to an AI. And the AI would give us very quickly saying, this is the damage, it's this size in this site, or even prognosis. In the future, this patient is going to recover for language or not. He's going to need this amount of language therapists and this specific treatment. So we can really march into individualized care and individual treatment for patients with aphasia. And that's the future we are working towards in our lab. And I would like you to take this opportunity to invite you to look at our lab website and the amazing work of language we're doing in the lab, and to contact us if you know any patients with aphasia or stroke. We have many studies regarding that. Follow us on socials. And I want to thank you, the CBU, for hosting, my lab members, and your brains for listening. Cheers to science. Thank you.